So let's touch on collinearity, and I guess points that are collinear mean they all lie in a straight line, basically. So we can see here from the diagram the point A, point, oops, wrong pen, point A, C, and B all lie in a straight line. So that really just means then that the vectors A and B and A and C are parallel. We can argue that AC and CB will be parallel. And in fact, they're all a factor of each other, okay? So I guess what we're looking at is the AC, where C is in the middle, is some factor of the whole length, AB, all right? So that's one definition. So if that's the case, so if C splits AB into a ratio or into a ratio, like it might be halfway, it could be a midpoint, it might be a third of the way along. So depending on what M is, if that's the case, then the rule for vector C is given by this. Okay, so that's often very useful to use. We don't have to use it to work it out, and I'll show you a couple of ways we can apply that. But vector C is 1 minus the ratio. So for example, if M was equal to, different pen, if we'll say it was the halfway, say it was the midpoint, well then vector C is just equal to 1 minus a half, which is a half A, plus a half B. If the vector C is A, B, we'll call that C. Say that's 1 to 2, so it's a third of the way. Well then vector C now, so OC if you like, if we've got our O down here. So vector C is equal to, the factor is a third, so a third, 1 minus a third is 2/3 of A, plus 1/3 of B. All right, so that's a nice rule to remember when we're working out different vectors, but as I said, there's ways and means around that. So let's have a look at this particular example. We've got vectors A, B, and C. So let's have a look at that. We've got A, B, and our point C will be somewhere. Well, there's vector O. So OA we said was A. OB we said was vector B. And vector C is going to float. So initially vector C is going to be the midpoint. All right. So, and we want to work out OC. So if I wanted to work out OC initially, one method would be to say that OC is equal to from O to A plus A to C, which is O to A plus. Now AC, because it was the midpoint, is a half of AB, which is equal to OA plus a half of AO plus OB, which is equal to OA plus a half of OB minus OA. So if we can group our terms together here, I get an OA plus a half OB minus a half OA. So I get a half OA plus a half OB, which is equal to a half A plus a half B, which is, come over here onto the right, what we said it was going to be if we just use that relationship to begin with. Okay, so you can see how it'll always work because we didn't give the vectors OA and OB any specific value. We just use the OA, AB, AO, OB properties, and that's where it evolves to. B, point of trisection. So I might rub out that C value there. Oh, not that one, I will. A point of trisection is basically, better go with green, is our vector split up into 3. AB nearer to A, so there's the point nearer to A. So it's actually what I alluded to a bit earlier, ratio of 1 to 2. So it's a third of the way along. So you can sort of see all the way in here, I could do exactly the same steps. Let's pick it up at OA is equal plus 1/3 of AB, which is 1/3 of OB minus OA. So we're sort of picking it up at this line here. So then we're going to get our OA plus 1/3 OB minus 1/3 OA, which is 2/3 OA plus 1/3 OB, which is 2/3 A plus 1/3 B, which again, over on the right hand side there, is what we thought it would be. Yeah. Running out of room. Part C. I guess we can still do the diagram, can't we? So let's grab a blue pen. AC is -2 times AB. So really AC must be, if that's AB, it's twice that size in the opposite direction. So C must be sort of out here somewhere. Blue's the wrong colour. Yeah, so C is the point out here somewhere. It's twice that magnitude and in the opposite direction. But we can apply exactly the same processes. Let's pick it up here, where for C, we have OA plus -2 times OB minus OA, which is OA plus -2 OB plus 2 OA, which is 3 OA minus 2 OB, which is 3A minus 2B. If I go to this rule here, where M is -2, I get the vector C is equal to 1 minus 2A minus 2B, which is 3A minus 2B. Okay, so that rule here isn't on any formula sheet. So it's one of those ones that you might need to remember if you want to avoid going through the longhand proof. All right. Yeah. So let's just extend that now into a little bit of proofing, which is just, look, if this is an 18-month process proofing, I think it's something that we find challenging, but we just need to practice it, all right? So to prove geometric results, the following properties are useful often. If A and B are parallel, then B is some factor of A, all right? Conversely, if we're told B is equal to KA, then they are parallel. So, you know, they work both ways. If the AB is equal to some factor of K times BC, makes them collinear, so they're in a straight line. If two vectors are perpendicular, that's a big one, their dot product is 0. So if and only if, so it's the only way two vectors can be perpendicular. And then if we were told the dot product is 0, that implies that the vectors are indeed perpendicular. A dot A is just mod A squared. All right, so let's have a look. Prove that the diagonals of a rhombus are perpendicular. So if we just draw our rhombus here as best we can, I probably could have done it a bit bigger. The diagonals of a rhombus. So if we call this vector A and vector B, I'll call that O, A, B, C. So we want to show that those diagonals are perpendicular. So let's work out some values initially for OA. So if I've got defining A and B like that, that means that, let's have a look, the vector OC is equal to, well, I can go from O to A plus B to C, which is equal to it should have been OB, B to C. So OB is vector B, and BC is the same as A, so that's just B plus A, all right? If I do the same thing for AB, I might go AO plus OB, which is OB minus OA, which is equal to B minus A. So now the dot product, OC dot AB, is equal to B plus A dot B minus A. So we can sort of see a difference of squares there, can't we? So that's equal to B dot B plus B dot negative A plus A dot B minus A dot A. Yeah? So B dot B up here, we see that's just mod B squared minus the negative sign's distributive, A dot B plus A dot B minus mod A squared. Now these two vectors cancel out, so I get mod B squared minus mod A squared. Now, since it's a rhombus, all of our side lengths are equal, which means the magnitude of A is equal to the magnitude of B. So therefore, it's equal to 0. Okay, and so our vectors are perpendicular. So that's the kind of thing that we need to do. All right, so draw a shape, define some vectors, and then we make use of properties. If we, different things that we need to do often are, if I can remember a few. We might have to show that a shape is parallel, and that they might tell you a property about the diagonals. With triangles, we might need to show that the points of bisection, so that's the midpoint, 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 all coincide there. Okay, so again, we're going to have to define some vectors. So it's just a slow process, practicing process, which is what 20E and 20F are about.